Hello and welcome to What's Up Physics. I'm Mariah.
I'm Aishwarya.
And today we'll be going over your very first lesson in AP Physics 1, Basic Motion. First, we will be going over the difference between distance and displacement. So distance is the length of the path that is taken by an object. Distance is a scalar quantity, which means that the direction the object takes does not matter. In other words, its distance will always be written as positive. And I'm going to model this on Mr. Rick Astley, who has so graciously offered to help us. So Rick starts at 0 on the number line and travels over to positive 4. What is his distance? Well, he went over 1, 2, 3, 4. So his distance would be 4 units. Now let's say that Rick starts at 0, and this time he goes over to negative 4 on the number line. What is his distance? Well, once again, he went over 1, 2, 3, 4. And so his distance would be positive 4 again. But now let's make things a little bit more complicated. Let's say that Rick starts at 0 and goes over to positive 4, over to 0, over to negative 4, and then back to 0. Now what's his distance? Well, let's see. He traveled 4 to get to here, then 4 to get back, then another 4 to get to here, and then another 4 to get back to 0. So that's 4, 8, 12, and 16 units is his total distance. Now let's talk about displacement. So displacement is how far away an object is from its starting position, and this is going to be in shortest distance. What does that mean? Well, shortest distance means that your displacement is equal to the length of a straight line you draw between your starting and ending position. And displacement is a vector quantity, which means that the direction you take matters. In other words, your displacement can be either positive or negative. And once again, we'll be modeling this on Rick Astley. So Rick starts at 0, and he goes over to positive 4. What is his displacement? Well, if I drew a straight line from 0 to 4, then it would be 1, 2, 3, 4 units long. But what is the direction of his displacement? Well, in physics, right and up are traditionally considered to be positive directions, whereas left and down are typically considered to be negative directions. Now, there are exceptions to this, where a problem will tell you to consider the leftward direction or the downward direction to be positive, something like that, But they would always spell it out for you. So typically you can just assume that right and up are positive and left and down are negative. But anyways, since Rick traveled to the right from his starting point, his displacement is positive 4. Now let's say that Rick starts at 0, and he goes over to negative 4 this time. What is his displacement? Well, if I drew a line starting from 0 to negative 4, its length would be 1, 2, 3, 4 units long. But what's the direction of his displacement? Well, he went to the left, and since that's a negative direction, his displacement is negative 4 units. Now let's say that Rick starts at 0 and he goes over to 4, over to 0, over to negative 4, and back to 0. Now what's his displacement? Well, his displacement is going to be 0 because he's at his starting position. In other words, he's not at all displaced from his initial position. Next, let's talk about speed and velocity. Any moment now. Okay, so speed is a rate that gives you the change in distance per unit of time. So I know that sounds like a lot of mumbo jumbo, so I'm just going to write out the equation. It's your change in position divided by the change in time. And what this gives you is your speed if you are going at the same speed for the whole duration of your trip. If you're traveling at different speeds, then what this would give you is your average speed. Now, speed is a scalar, which means that the direction you travel in does not matter. Whichever way you go, your speed will always be written as positive. Now, velocity is your rate of change in displacement per unit of time. So the formula is going to be the same. Change in position over change in time. And again, if you're not going at one velocity for your whole trip, then that's going to be your average velocity. Now, the difference between speed and velocity is that velocity is a vector. So, depending on the direction you travel in, it could be positive or negative. If you're going right or if you're going up, positive. If you're going left or if you're going down, negative. Now let's talk about instantaneous speed or velocity. So this is your rate of change of distance or displacement, depending on whether you're talking about speed or velocity, at an instant in time. So this would be an object's speed or velocity at one particular moment, like for example, at exactly 3 seconds into an object's motion. And instantaneous speed or velocity typically comes up more when you're talking about an object that is not traveling at a constant speed. Okay, now let's talk about magnitude. So if a problem asks for the magnitude of something, it's only asking for the amount and not the direction. For example, let's say you have to find the magnitude of the velocity of an object, and you find that the velocity is -4 meters per second. What you would do is drop the negative sign and write your answer as just 4. Basically, you can disregard direction and write your answer like it's positive.
Alright, so now we're going to talk about acceleration. So acceleration is the change in velocity per unit of time. Now, if your velocity is not constant, no matter whether you're speeding up or slowing down, you have some amount of acceleration, which it can be either positive or negative, and we'll explain the difference in a bit. But first I want to make a quick note. We don't use the term decelerating in Physics 1. We use the broad term acceleration for all changes in velocity, even slowing down. So don't get confused with that term. So now let's take a look at our units. The units for acceleration are meters per second squared. Why is this? Since acceleration is the change in velocity over time, our units are the change in meters per second, which is velocity's units, per second. And a quick side note, we use meters in Physics 1 for distance and seconds for time. So if you actually math this whole thing out, it translates to meters per second squared. But it might be easier if you conceptually want to think of the units as meters per second per second. So acceleration is a vector just like displacement and velocity. It has direction. But don't make the mistake of thinking, if an object is speeding up, it has positive acceleration, and if it's slowing down, it has negative. That is not necessarily true, and you'll see why in a minute. Another mistake you don't want to make is thinking, oh, if Bob is running in the positive direction, he has positive acceleration, and vice versa. That is also not necessarily true. So what is the direction of acceleration? So acceleration points in the direction of the change in velocity. What does this mean? Well, say we have Bob, and he's running 5 meters per second to the right, which is the positive direction. Then he slows down to run 3 meters per second to the right. Well, by how much did Bob's velocity change? You might be tempted to say 2 meters per second, but the change in velocity is actually the final velocity minus the initial. So that would be, in this case, 3 meters per second minus 5 meters per second, which is -2 meters per second. Since the change in velocity is negative, that means acceleration is also negative, and it points to the left behind Bob. In AP-style questions, though, you most probably won't be given neat numbers like this example where you can easily calculate acceleration's direction. You want to be able to know which direction it points even if you're given a scenario with no numbers. So to do this, we're going to model the velocity vectors of a scenario as arrows, which the velocity vectors here are 5 and 3. Well, what do I mean by that? We'll do some practice problems, but first I'll show you how to model velocity vectors. So you can visually model velocity by drawing an arrow that points in the direction of the velocity and has a length proportional to the magnitude of velocity. For example, car A's speed is bigger than that of car B's, so its arrow would always be bigger than car B's. However, if we say, for example, car A was going in the negative direction, or left, its arrow would be pointing in the opposite direction of car B's, like so. Alright, let's do some problems now. Example number 1. A guy is exiting the freeway and he gets onto the off-ramp, so he's slowing down. He's traveling towards the right, which is the positive direction. Which way does his acceleration point? So our guy Bob starts by traveling some speed to the right. Let's call this VO, which is V initial. Then he slows down, but he's still traveling to the right. So let's label this and call it V final. And it'll have a less magnitude than the initial velocity. Now, we know that the change in velocity is what you add or subtract from the initial velocity to get to the final. Since Bob is losing velocity, his change in velocity is going to be negative. Now, we also know that change in velocity, the direction of change in velocity, is the same as the direction of acceleration. So since this direction is negative, acceleration's direction is also negative, and it points left. Example number 2. A guy is going from the on-ramp onto the freeway, which means he's speeding up. He's traveling to the right, which is the positive direction. Which way does his acceleration point? So now, Bob starts with some positive velocity. We'll label this V initial, or VO. And then he gains speed, which means the magnitude of his final speed is greater than his initial, hence the longer arrow. Now, again, the change in velocity is what you add or subtract to the initial to get to the final. Since Bob gained speed, his change in velocity is going to be positive, which means his acceleration is also going to be positive, pointing to the right, because they both have the same direction. However, in that problem, acceleration wasn't positive just because the guy is speeding up. For example, let's take this whole scenario and switch it so that he's moving to the left instead of the right. It's a pretty similar scenario. His starting velocity might look something like this. His final velocity might look something like this. But his change in velocity, what we're adding to the initial to get to the final, is going to be negative. This goes to show that just because something is speeding up doesn't mean it has a positive change in velocity / acceleration. In this scenario, this guy is speeding up, but he has a negative change in velocity because he's going to the left, or the negative direction. Now let's modify that scenario. Let's say Bob is still moving to the left, but he's actually slowing down. So he would start with some high negative velocity, like so. And then he would come to some lower negative velocity like this. Now, since the change in velocity is what we add or subtract from the initial to get to the final, if we're going from a high negative to a low negative velocity, we have to add some velocity. Therefore, your change in velocity would be positive, and so would your acceleration. This goes to show that just because Bob is slowing down doesn't mean he must have a negative acceleration. In this case, he has a positive acceleration. Example number 3. Mariah, who is super late to school, which is a common occurrence, is running to make it in time. She's running to the right when she realizes that she left her homework at home. She turns around and runs back to her home, going the same speed as before. Draw her acceleration vector. So before we start this problem, there's one key term that you have to notice. She turns around. Whenever a person or an object turns around or changes the direction of their motion, they briefly come to rest. And we're going to show you a video of Mariah running to prove this. So you can see in this video, Mariah starts with some positive velocity. As she gets closer and closer to the tree shadow, she slows down until she comes to momentary rest right there. We can see that she didn't cover any displacement for that moment in time as she turned. Then she started speeding up in the opposite direction. Whee! Okay, so let's apply that to Mariah here. We know that she first starts with a positive velocity. We'll label that V initial. VO. And then she slows down, comes to a rest, and then goes back in the negative direction, but she ends up at the same speed. So her VF is going to be equal in magnitude to her VO. Now, to get from that initial positive velocity to 0, Mariah had to undergo a negative change in velocity that is equal in magnitude to her starting velocity. In other words, that negative change in velocity would cancel out her initial velocity and bring her to 0. Then, to get her from that rest position to her final negative velocity, she has to undergo that same change again. Mariah's change in velocity, therefore, is equal to double her initial velocity. However, it points in the negative direction, so her acceleration is also negative.
Alright, now let's do some practice problems. If you want to go ahead and try them on your own, then when we show you the problem, you can go ahead and pause the video and just check back with us for the answers. Okay, example number 1. So for part A, we need to find the x distance traveled from t equals 0 seconds to t equals 2 seconds. This means you can ignore this vertical bit, just focus on the horizontal. Okay, so t equals 0 to t equals 2. We're going to go over 1, 2, and 3. So the distance you traveled is 3 meters. Now we're going to do it from t equals 0 seconds to t equals 4 seconds. So we're going to go over 1, 2, 3, 4, 5, 6, 7, 8. You traveled 8 meters. Now we're going to do it for displacement. So we need to find the x displacement traveled from t equals 0 seconds to t equals 2 seconds. So starting from t equals 0, you go over 1, 2, 3. So your displacement is positive 3 meters. And then you need to find your x displacement traveled from t equals 0 seconds to t equals 4 seconds. So you start from here, right? And then you end here at 4 seconds. So you're just going to find the shortest distance from your starting point, which is this, to your ending point, which is this. So you're going to go over 1, 2, so that's in the negative direction, so your displacement is negative 2 meters. Example number 2. A kangaroo is released in your classroom, causing many students to scream. The kangaroo jumps 1 meter, then waits for 30 seconds before taking another 1 meter jump. This jump, rest, jump routine lasts until the kangaroo has hopped across the classroom. Doing this, the kangaroo takes 10 minutes to travel 20 meters. What is the kangaroo's average speed in meters per second? Okay, folks, so when we're talking about speed, that is going to be placed in units of meters per second. But for the time that it took to go across the classroom, the kangaroo took 10 minutes. They give us the time in minutes, so we need to convert that to seconds to solve this problem. So a quick lesson in conversions. Whenever you want to convert something, you put the thing that needs converting, in this case 10 minutes, over here. And then you're going to need to multiply that by something that is equal to 1. Why? Well, whenever you multiply a number by 1, you're going to get that same number. And we do want that 10 minutes, it's just that the units need to be in seconds. So we're going to multiply it by a fraction, and in the denominator, I'm going to put the unit of minutes so that the minutes cancel out. And then on the top, I'm going to put something with the units of seconds so that we get to keep the seconds. So I'm going to put 1 minute on the bottom and 60 seconds on the top. And this thing is equal to 1. So when we multiply it to those 10 minutes, we're going to get the same number just in seconds. So you multiply 10 and 60, and that gives you 600 seconds. Now we need to find the kangaroo's average speed. So if you remember, speed is equal to the change in position over the change in time. So that's going to be 20 meters over 600 seconds, which is going to be equal to 0.0333 meters per second. Part B of example number 2. Why is it more accurate to say average speed rather than just speed? Well, if we use the word speed, then we're implying that the kangaroo was consistently moving at 0.0333 meters per second. But the kangaroo was sometimes moving and it was sometimes at rest. So it can't have been moving at that speed all the time. Now, if you use the word average speed, then you're just calculating the speed at which the kangaroo would go to cover 20 meters in 10 minutes if he was going at a constant speed. In other words, it's the average of the various speeds that he was traveling. But since the kangaroo was traveling at various speeds, we should not use the word speed, because that makes it seem like he was going at that speed the whole way through, which is not the case.
Example number 3. You hop on a random bus to get to Rick Astley's concert. The bus is traveling at a speed of 20 meters per second. At some point, you realize the driver is actually going towards Mick Chasley's concert. Rick's is in the opposite or negative direction. Mick's concert is 1,000 meters away from your current position, but if you go at this speed consistently, you can get to Rick's concert in 1.5 minutes. Which concert is a greater magnitude of displacement away from your current position? So what they're basically saying is, if you travel at the speed we're going right now, 20 meters per second, but in the other direction, then we can get to Rick's concert in 1.5 minutes. However, they are just asking for which concert is a greater magnitude of displacement away from our current position, so we don't really need to think about velocity or direction. We can just take the speed and run with it. So we learned from earlier that displacement over time is equal to velocity, or rather, change in displacement over change in time. So this means that velocity times time is actually equal to displacement. And hey, we have both velocity and time right here. So let's multiply them together. We have 20 meters per second, which I said velocity, but we're disregarding direction, times 1.5 minutes. But they're trying to trick you here by giving us the time in minutes when we really need it in seconds. So we're going to multiply this 1.5 minutes by an expression that's equivalent to 1. So we're going to have the minutes at the bottom because we want them to cancel out. 1 minute is equivalent to 60 seconds on the top. Now, by multiplying 1.5 by this expression that's equivalent to 1, we can cancel out minutes and convert everything into seconds. Now we can also cancel out seconds, leaving our unit in meters, which is what we need because we're looking at displacement. and that multiplies out to 1,200 meters. So, Rick's concert is a greater magnitude of displacement away from our current position than Mick's. Example number 3, part B. Would your method for finding the displacement of Rick's concert from your position have worked if you weren't going at a constant speed? Why or why not? So think about this for a second. No, our method would not have worked, because if the bus didn't travel at a constant rate, it would be covering different amounts of displacement every second. When we multiplied the bus speed by time, we did so because we knew the bus would continue at that uniform speed. So we knew that there was a set amount of displacement covered every second that wouldn't change, which made our calculations accurate. Part C. Describe the bus's motion during the trip if its average velocity is equal to its instantaneous velocity for the whole ride. So pause the video and think on this for a moment. Okay, recall that instantaneous velocity is an object's velocity at a particular moment in time. The problem says that average velocity equals the instantaneous velocity throughout the whole ride, which is to say at any moment in time throughout the ride. If the instantaneous velocity of the car is the same throughout the ride, the car must be traveling at a constant speed and also must be maintaining the same direction throughout its motion.
Thanks for watching our video.
Our next lesson will be on graphs.
If you like this video, please consider liking, sharing, or subscribing.
Bye for now!